So using all the things that we have learned, we are looking at something called as Poisson's formula. So what is the formula about? The formula provides information on the volume of liquid flowing out per second through a horizontal pipe. Okay, so you have a horizontal pipe. The rate at which a fluid comes out, a liquid comes out, a liquid flows, we can figure out with the help of Poisson's formula. So this set of assumptions that we make, the flow of liquid is steady and parallel to the axis of pipe. The pressure is constant over any cross section of the tube. So there is no hole or anything per se. There is no loss of pressure. The liquid velocity is 0 at the wall of the tube and increases towards the axis of the fluid. This we have seen. Okay, the liquid velocity is 0. That is, the liquid gets stuck to the walls of the tube. And as in when we go to the center, it increases. Right? You have seen this with your velocity profiling and all of that. Right? The tube is held horizontal so that the G does not influence the flow of the liquid. Acceleration due to gravity is not going to influence it. So we're looking at this particular derivation. So for that, we have to make use of few commonsensical stuff. So first thing is, do you think viscosity plays a role over here? Q is your rate of flow of liquid, right? Now, do you think viscosity plays a role? Yes, it plays a role. To what power, we don't know. Do you think the radius of the pipe plays a role? Yes, it does play a role. Do you think the pressure plays a role? Yes, that also plays a role. Pressure per unit length. So the rate of flow depends on quite a few factors, and all of those factors are over here. Okay, where R is your radius. P by L, actually P by L, let me show that to you. So if this is a pipe, if you have a pressure over here, say P1, and say this is P0 or PA and PB, let me write PA and PB. If this is L, the difference in pressure, I'm writing it as P actually over there, is nothing but your PB minus PA. If the water is coming out from here, it is PA minus PB actually. Pressure will be more over here. And L is the length. So if I pressure per unit length, it becomes gradient of pressure in some manner. Okay, so that's what P by L stands for. So we have pressure gradient. Let me just, okay, so this is pressure difference. If I divide with L, this will give us, actually this is small l, this will give us pressure gradient. Okay, so now we will use dimension analysis. Using dimension analysis. So can you tell the LHS? LHS, what is the dimension at the LHS? So we have volume by time, rate of flow, right? Volume by time. So volume is your cube, time is -1. So that would be your LHS. Now we're looking at RHS. So RHS, there is R, which is nothing but L, dimension of R is L. Then dimension of P by L is M. Pressure is force per Yeah. And divided by L will be L over here. So all in all, we have ml minus 2 t minus 2. You have to remember a few of the dimensions. Pressure, you guys can derive this out. Okay. You will end up with this. And you have your coefficient of viscosity. So that is ml minus 1 t minus 1. This, guys, I have it in front of me. I don't remember this. I knew that I don't remember, so I looked it up and I'm writing. No, you can't know everything, right? Now, so on substituting these dimensions, to 1, what we're looking at is L cube t minus 1 will be equal to, yeah, 1 by 1 we have to do it. R is A. Then we have, this is ml minus 2 t minus 2 b is what I have called it as, and this is C. We have 3 NOs, we need 3 equations, and we are done. Okay, so let's do it. So LHS is LHS, and RHS we have L. We'll start with L, or start with, yeah, L. No, we can start with M. M B plus C times of L A minus 2B minus C times of T minus 2B minus C. Okay. So now you can equate the power and solving. So what we have here is B plus C is 0. So B is equal to minus C. That's from M. Then you have A minus 2B minus C is equal to 3. And you have minus 2B minus C is equal to minus 1. So from here, if I substitute and all of that, I'll get plus B. B is equal to 1. So therefore, B is equal to 1. Then C will be equal to minus 1. And A will be equal to, yeah, have a look at it. This is 2, this is 1 and 4. Okay. So your rate of flow will be, where is it? Will be not equal to, sorry, proportional to r to the power of 4 if I'm right, r to the power of 4. So radius plays a big role. R to the power of 4. Then P by L to the power of 1. And coefficient of viscosity inversely proportional. Makes sense. So when we remove the proportionality constant is equal to pi by 8 times of all of this set of expressions. And that's your formula. Yeah, it reflects right. Okay, guys. So what is that we are looking at? We are looking at a formula wherein the LHS talks about how much water is coming out of a pipe, which is placed horizontal. And it's given by this particular expression, and we did it with help of dimension analysis. The certain condition we took up and then we solved it. You can look at the conditions over here. And after that, it's kind of commonsensical. Of course, viscosity plays a role. If it's highly viscous, then the rate of flow will be less. It's like if I take a bottle, if I squeeze, okay, let me take 2 scenarios. If I take 2 similar bottles, like say ketchup bottle kind of scenario, one I fill it with water, another I fill it with honey. If I press them both with equal amount of pressure at the same space and all of that, what happens? Which squirts out more, or which travels the furthest away? Water, right? So that's what we are looking at, right? So that's what we are looking at. And that effect, we have to make use of such commonsensical things, and you'll end up with different expression. So in this case, we are looking at volume related to viscosity. So more the viscous, less volume comes out. I hope that is commonsensical as of now. And the same thing came out with the derivation as well. See, it works. Maths and physics and everything works. And obviously, we look at pressure difference. If I squeeze harder, more water comes out. Common sense. And also radius. If I have a big pipe and if I do that, it will not come out to that extent. But if I have a chunumunu small piece of pipe, mouth and all of that, if I squeeze with the same amount of force, it squirts out and goes to a larger distance. Commonsensical things. All of these are commonsensical things. Okay. So with that basic understanding, we'll be able to figure out the relationship using your dimension analysis. And we end up with the formula. And that is your Poiseuille. This formula. I don't want to pronounce it. I did pronounce it, but now I just lost the confidence. Okay, yes, you can pause and have a look.